Hello guys, this is Prime Concept. In this video, we want to consider the purely inductive circuit as one of our considerations under the AC circuit analysis. Now, in our previous videos, we introduced AC circuits, we've considered purely resistive circuits, we've considered purely capacitive circuits. So we want to look at purely inductive circuit. Now, like the name implied, purely it simply means a circuit that contains only an inductor. That is a purely inductive circuit. So we can denote that circuit with this circuit diagram. So this, you should take note that the symbol for inductance of an inductor is capital letter L. So that is that. And then this is the current I through the circuit. This is the AC voltage source, and the voltage is given as this. So these are purely inductive circuit, right? Now, very quickly, we want to mention an important point, which when we make a derivation we're going to make in this video, we're going to point it out from the derivation. But let's first mention it before going into the derivation. So for a purely inductive circuit, voltage leads current by a phase angle of 90 degrees. So you take note of this. For a purely inductive circuit, voltage leads current by a phase angle of, you can say, 90 degree, or pi over 2 radian, which is same as 90 degree, or you can say 1 over 4 of a circle. So any of this will go. But the major concept here is that voltage is always ahead of what? Current. And by what amount or by what angle does it lead current? It leads it by 90 degree. Or you can simply say that current lags behind voltage by the same amount of 90 degrees. So this is one thing we should know. Now, very quickly, if there's a phase difference between voltage and current of 90 degrees, then it means we can draw a Phasor diagram that shows this phase difference, or a vector diagram, what we know as vector. So let me call it Phasor diagram. I can still call it vector diagram. Now I want to take current as my reference. So I'm going to draw current on the x-axis. Anytime you're taking any quantity as your reference when drawing your phasor, it means that that quantity will be on your x-axis, positive x-axis. Now, since voltage leads, and this is my current, it means that I should take my voltage up, which is VL. This is 90 degrees, then this is the direction of motion, counterclockwise. So this is my phasor diagram for a purely inductive circuit. Now, we can still take voltage as a reference. It means we're going to draw voltage on the x-axis. Remember that voltage leads. It means if I want to draw my current, rather than going up, I'm going to now go down, telling you that voltage is ahead of current, since this is my direction of motion, counterclockwise. So any of these two phasors would be telling us the same thing about both of them. So quickly, we want to mention the wave diagram for a purely inductive circuit, the wave diagram. The wave diagram would be given like this. So I would have my voltage. Let's say my voltage is starting from the origin this time. And I can have my current to start this way, and so on. So this is going to be my voltage. This is going to be my current, right? So this is my waveform or wave diagram for my purely capacitive circuit. So you can see that this is the peak, and that is where this distance in angle is measured as 90 degrees or 5 radian, because at this point what you have is 90 degrees. So it means that the phase angle is 90 degrees. Now, quickly, we want to do a derivation that is very important in purely inductive circuits. So, but let's mention the term before we start the derivation. We have what we know as inductive reactance. Inductive reactance is denoted with the symbol X subscript L. This is the symbol for inductive reactance. So in a simple way, inductive reactance is just the resistance of an inductor. That is inductive reactance. It is resistance, but this time around, this resistance is provided by an inductor. It's the resistance that is present in the coil that forms an inductor. That's what we call inductive reactance. So we can simply say that this is the opposition. This is the opposition to the flow of current in an AC circuit offered by an inductor. So that is that. Now, since this is actually a resistance, what is the unit? Of course, the unit of XL is actually ohms. It's actually ohms. So it is a resistance, so it is measured in ohms. So it's very important to take note of it. Inductive reactance XL is not the same as inductance of an inductor. So XL is different from L. These are two different things. While this one is measured in ohms, this is inductance of an inductor. It is measured in the unit of Henry. So don't mix up the two. So once you see your options, it can tell you which of these quantities you're trying to find. Now, how does this connect with our circuit? So we want to do a simple analysis. So we want to derive the formula for finding XL. So there must be a relationship for finding or calculating the size of XL. So how do we do it? Let's recall. We'll recall that the voltage across an inductor is given as V, which is equal to L, the I, the T. So the voltage is given as this, right? Where L is inductance. This is very similar to capacitance relationship. So check my previous video on that capacitance, you will understand. So if the current, we denote the current I as a sine function, sine omega t, then it means I can get back to this and differentiate. So I'll have that my voltage V would be equal to L. I'm differentiating I naught sine omega t, right? Yes, so I would have that V would be equal to, I can bring I naught out as a constant. So I would have I naught L d dt of sine omega t. This is what I want to get. So I have that V would be, now if I want to differentiate this, just like we did in our previous video, you differentiate omega t first. When you differentiate omega t, you would get omega. So I have I naught L omega. Then when you differentiate sine, you get cos. Then you write omega t. So it means that my voltage V is given as this. Now remember, for the cosine relationship, you can still say that V, if I want to write this voltage in terms of sine function, I can still say that V is I naught L omega sine what now? Sine omega t plus 90, right? So this sine omega t plus 90 is still the same thing as cos omega t. Why is it the same? If you use your compound angle relation, you see that it's the same. So this relationship would simply tell you that voltage is ahead of current by a phase angle of 90 degrees, and that is what we mentioned earlier, that for a purely inductive circuit, that the voltage leads current by a phase angle of 90 degrees. So, and you can see that, but this is not where we are going. I want to derive something else. So from what we have arrived at, our voltage relation, which is any one of these, well, let me go with this. Both of them are now, they are the same, but let me go with this for simplicity. So this, you can say that V generally is actually V naught cos omega t. So if you say this, it would simply mean that your peak voltage is equal to this whole quantity behind your cosine by comparison. So I can say V naught peak voltage would be equal to I naught L omega, right? So I want to divide both sides by I. I'll divide by I naught, divide by I naught, so that I have V naught over I naught equals what now? This would go equals L omega. Now remember that voltage divided by current is actually a resistance. But because in this circuit we have just an inductor, it means that the resistance is the resistance that is provided by an inductor. And what do we call that resistance? Inductive reactance. So I can simply replace this with what now? With X subscript L, which is now equal to what? L omega, right? Yes. And you still know that omega is what? 2 pi f. So I can still say that XL is equal to 2 pi fl. So it's either I use this relationship or I use this one, depending on what I'm given in a particular question. Now, just like we mentioned also for capacitors, you can see from our final relationship there that the inductive reactance is directly proportional to the frequency. So meaning that in this particular case, when frequency increases, your inductive reactance would also do what? Increase. When frequency decreases, your inductive reactance would do what? Decrease. When frequency is zero, your inductive reactance would be what? Zero. So these are points you should note. And the graph for XL against frequency would be a linear relationship that starts from the origin. So this is what you would have as the graph of XL against F. So I've pointed out a whole lot of things under the purely inductive circuit. So before we end this video, let's take one example to buttress our point. All right, now let's take this quick example and then use it to draw the curtain in this video. So the question says, at what frequency will an inductor, so we are looking for frequency, at what frequency, so let's call it F, will an inductor with inductance of 10 milliampere, so it means that L is 10.0 millihenry, sorry. Now, first thing you want to do is to know that you have to remove this milli, and milli is 10 to power minus 3. So it means I can say that L is 10.0 times 10 to power minus 3 Henry, which for short, I can just say that L, this 10 is same as 10 to power 1, so 1 minus 3 is minus 2, so I can just say 10 to power minus 2 Henry. Now, at what frequency will an inductor with inductance of this have a resistance of this? So they are telling us what frequency will give this inductor a resistance XL of 8,000 ohms. That is just what they are asking us. So this time we want to find frequency. What is the relationship we know? We know that XL is equal to 2 pi fl. So I'm trying to get frequency. So I would make frequency the subject. So frequency becomes XL divided by 2 pi L. So this is what I have. So that my frequency would be XL, which is 8,000 divided by 2 pi. I will leave my answer in terms of pi. So that is how it is in the options from where I got the question. So L is 10 to power minus 2. So my frequency is simply going to be 8,000 divided by 2 is 4,000. So I can just say 4,000. Instead of 4,000, I would say 4 times 10 to power 1, 2, 3, 3. 3 minus, okay, 3 plus 2 is 5. So 4 times 10 to power 5. 4 over pi times 10 to power 5. So that is what I would have as my answer. So I believe that this is clear. So and what is the unit of this frequency? It is actually hertz. So 4 times 10 to power 5 over pi. You can say 4 over 5, 4 over pi times 10 to power 5. So I believe that this concept is really clear to you. So if you have watched this video up till this point, please do well to hit the subscribe button. That is a way of showing me your support. Like this video, comment, and share with 10 of your friends. Tell them it is prime concept. I'll see you in my next video. Thanks for watching.